So in addition to what we covered in the last lecture, in lecture 8, a competitive model, we went over the cooperative model a little bit. So I want to, again, I mentioned earlier, I want to break it down into two completely different lectures. In lecture 8 only focus on competitive model, and in lecture 9 focus only on comparative models. There are two comparative models that I want to talk about. The first one is with unconstrained growth, and the second one is with logistic growth. Okay. Again, the setup will be very much the same for one another. The only difference is from the first assumptions. So in the case of cooperative model with unconstrained growth, the first assumptions, we have both species experience unconstrained growth when there is the presence of one of the other populations. Okay, so in this case, you have pollinators and plants such as bees and flowers. All right, so every other setup should be the same. Again, the only difference between this model that we're going to go over and the model with logistic growth is going to be the type of growth that they have in the presence of the other species. So in this case, you have F sub n is the populations of flowers at time period n, and capital B sub n is the bee population at time period n as well. So similar to the case of prey and predator model and competitive models, without the presence of the other populations, the one populations of considerations can grow exponentially, right? That is in the populations of flowers. You have f sub n plus 1 minus f sub n equal to k1 times f sub n. Right, without the presence of the other population, without the presence of the bee populations, the flower population is assumed to increase exponentially using this model. This is different equations that we see many times already. Now, in the presence of the bee populations, you're going to have plus k3 times, let me use alpha f sub n times b sub n. Alright, so for K1 is the growth rate of flower populations. And we assume K1 to be a positive number. And alpha, in this case, the benefit coefficients that flowers receive from bees. And we also have to make the assumptions that alpha is a positive number. So for bees, the bee populations, b sub n plus 1 minus b sub n equal to k2 times b sub n. In the absence of one population of the flower populations, the bees are supposed to increase exponentially. But if there is the presence of flowers in the ecosystem, then you add in the term beta times f sub n times b sub n. In this case, k2 is the growth rate of bees populations. And you assume K2 to be a positive number. And beta in this case is the benefit coefficient that bees receive from flowers. And you also assume that beta is a positive number. So the value of alpha and beta, they are benefit coefficients. So in the case of alpha, this is pollinations, enhances reproduction. And beta, more flowers, provide more food. Right, so that is the setup for the flowers population and for the bees population. Okay. Now I'm going to take these two equations. Again, I'm going to name this equation equation 1 and this equation equation 2. And from equation 1 and 2, we have the system of different equations of the form f sub n plus 1 minus f sub n equal to k1 times f sub n plus alpha times f sub n times b sub n. And b sub n plus 1 minus b sub n equal to k2 times b sub n plus beta times f sub n times b sub n. Now the next step is to find equilibrium values from the system of different equations that we got here. So to find equilibrium values, we substitute f sub n plus 1 equal to f sub n equal to f, and b sub n plus 1 equal to b sub n equal to b into the system of different equations. Right. So from the first equation, again, I'm going to break the paper down into two different columns. One column I'm going to work with the first equation. In the second column, I'm going to work with the second equation. So from the first equations here, I get f minus f equal to k1 times f plus alpha times f times b. So on the left hand side, you get 0. And on the right hand side, f is a common factor. and you'll take out f, and you're left with k1 plus f times b. And here you get value, one value that is f equal to 0, or k1 plus alpha times b equal to 0, or b is equal to negative k1 over alpha. It's a negative population at this point. Hold on to that. Okay. Now I'm going to move on to the second equation and see what happened. So b minus b equal to k2 times b plus beta times f times b. On the left hand side you got 0 as well. On the right hand side you have b as a common factor, one time k2 plus beta times f. Right. So one case you have b equal to 0, and on the other case you have k2 plus beta times f equal to 0. For this equation you get f equal to negative k2 divided by beta. So you have two equilibrium points. One point is 0, 0. The other points are negative points, and does not make sense for the population dynamic because the populations cannot be equal to negative number. It can be equal to 0, the population died out. We obtain two equilibrium points. So 1f comma b equal to 0, 0. This is the trivial solution. So our populations will die down from the ecosystem. Right. And another equilibrium point f comma b equal to negative k2 over beta comma negative k1 over alpha. So non-trivial solutions. So this one is not possible. Okay, so this is not a possible model to have. Now what can I change in order to make this model possible?
Make it positive.
How can I make it positive? Yes, we're going to make it positive, but how can I make this positive?
Times by negative number.
True, true. But what kind of assumptions that I need to make in order to turn this from a negative value, which is impossible, to something, to a positive value, which is possible? What am I missing here? Think about reality. What happened? Now you have flowers, now you have bees. What happened? There's no flowers. What happened to the bees? They died. Without the bees, what happened to the flowers? They died. Alright, so instead of this model, these two assumptions, that the populations will increase exponentially in the absence of the other populations. Instead of exponential growth, you change that to exponential decay. You with me on that? Okay. And similarly for the second equation, instead of letting the b go to positive infinity or increase indefinitely, you can say that in the absence of flowers, b will die. And that makes sense in reality. Okay. So that's the one modifications that, or the two modifications that you need to make in order for this model to make sense. You okay with that?